All right, it is week 14. We are nearing the end. This week we're looking at lessons 112, 13, and 14. So those three lessons. So let's go ahead and flip over to 112. So in this lesson, we're looking at applications of the Pythagorean theorem. So people students' questions are, when are we going to use this? When are we going to use this? Well, you'll use math in your everyday life. Specific formulas, maybe in your career choice, you may not use on a daily basis. But the Pythagorean theorem is one that you guys probably know by heart, and it can be used in a lot of different ways. We can use it to find indirect measurements, as we've talked about, using shadows and things like that, versus trying to calculate these measurements, which would be near impossible or difficult to do. There's some other principles that we can apply to it as well. So the Pythagorean triplet, 3, 4, 5. 3 squared plus 4 squared is 25. Square root of 25 is 5. So this is a Pythagorean triplet. We can multiply that by 2, 3, 4, 5, whatever, and it's going to remain the same. 6, 8, 10, and we multiply these numbers by 2, and we multiply these numbers by 3, and we multiply these numbers by 4, it remains the same. And why is that important? Well, there is a way that we can use this to make sure that something is a 90-degree angle. Because let's say you're building a house or a structure or a wall or something, and you want to make sure that you're sure that everything is square and at 90 degrees. Well, you can use this to help find it. Again, we don't want it to be at 89 or 91 or 92. We want it to be exactly 90 degrees. Well, we can use one of these Pythagorean triplets to help us out. So let's say we don't want to get down with a protractor or maybe with a t-square or something like that, but we want to be sure that this is 90 degrees. Be slightly off because everything else in the house or whatever we're building is going to be thrown off as well. So if we measure 3 feet or inches, probably feet would be better so that way it's a little bit more accurate. 3 inches versus 5 inches, and one little pencil mark to the right or the left could throw you off. But anyways, so we measure 3 feet here, make a mark. And we measure 4 feet here, we make a mark. And then we measure the diagonal from the mark to the mark, and it should be 5 feet 0 inches, exactly. And if it's not, we know without even getting anything into this corner here to see if it's square, we know that it's not 90 degrees. Could be a little bit more, a little bit less, but we need to make sure that it's straight. So that's an application of, we can use the Pythagorean theorem to check our work. And again, you guys kind of do this with pencils and a ruler or something if you wanted to, just to kind of mess around with it. So example 1, 5, 12, 13 are Pythagorean triplet because 5 squared is 25 plus 12 squared is 144, which equals 169. Square root of 169 is 13. It's a triplet. To find the next 3 multiples of 5, 12, 13, we multiply by 2. So 5 times 2, 12 times 2, 13 times 2. By 3, 5 times 3, 12 times 3, 13 times 3, and then by 4, same thing. So that's how, it's just like a scale factor. We're just multiplying them by 2, all of them by 2. We're not changing the length of one and not the other. They're all going up at the same proportional rate. Multiply by 2, 3, and 4. A roof is being cut over a 24-foot wide room. The slope of the roof is 4 inches, is 4 and 12. Calculate the length of the rafters needed for the roof. And so we have this here. We have goes up 4 and over 12. We want to figure out the length of the rafter. Let's see if we can triangle. It's something like that. So we have this rafter. We're told that we're up, we're over 12, and up 4. This is 24 feet down here. And we'll find the length of this rafter. I don't know if it's a 412 roof for every 12 inches it's going. For every foot it's going down 4 inches or up if we're going this way towards the peak. But what we can calculate to find this length, and if it's 412, well, we know that this would also be 4, half of this would be 12, so a 412, we could look at this as a right triangle, or this one that we have drawn out here. Either way, they share the hypotenuse that we're trying to measure, which is the length of the rafter. So we're going to use the diagonal thing. 4 squared plus 12 squared equals the length of the rafter squared. So 4 squared is 16 plus 44, 12 squared. We get 160. And then we take the square root of that. And we get, so we did, I messed this up in that error. So we did 4 squared plus 12 squared, 160. And then we take the square root of that. And then for purposes of measurements, if I said, oh, I need, what could we say that? 16, so 4 root 10, we could break that apart too. If I said I need square root 160 feet aboard, or 4 root 10, we'd go, what? That doesn't really make sense. So in this example, I know in the past we've said don't calculate this out, reduce it down and keep it in a root form. But if we're building something and we need a measurement, then we're going to have to round it to some point. So 12.64911, we would round it off at some point. Look, I think they rounded off to 12.65. So it's about that. Using the calculator, then we were told to include 2 feet for the rafter tail, so 12.65 plus 2, 14.65 feet, 14 feet, and then 0.65. We could, because again, since we don't really use decimals for feet and inches, we use fractions, we could use a unit multiplier to get that to be 14 feet, 7.8 inches, which they rounded up to 14 feet, 8 inches. All right, Serena went on a level field to fly a kite. She let out 200 feet of string and tied it to a stake. Then she walked out on the field until she was directly under the kite, 100 feet. We want to figure out how high is it. Well, again, we can use the Pythagorean thing, 150 feet squared plus this other leg, or the height of our kite squared, equals 200 squared. If we want to B and our C, again, we know the hypotenuse in this example, which is fine. We have 2 of our 3 measurements. So we plug them in. That gives us 150 squared is 22,500. Subtract that from both sides. 200 squared is 40,000. We get 17,500. We take the square root of that, and it's right about 132 feet. Okay, we will do that practice set together when we get to class. All right, in this lesson 113, we're looking at volume of pyramids, cones, and spheres. And these are all on your reference sheet. Again, we think about a pyramid, it can be any polygon at the base. Usually we think of a square base, like the Egyptian pyramids, or some of the ones we've kind of imitated here in the United States, like the Luxor and some of these hotels and shopping centers and things like that. So the volume of a pyramid is 1/3 the volume of a prism that has the same base and height. So we watched the What's Your Problem video where they showed this property by filling up water, and I think they used cones and a cylinder, which will be the same kind of concept as we'll see in a minute. So imagine this wasn't coming to a point and it was a rectangular prism. Well, the pyramid created out of that has the same height and the same base is going to have 1/3 the volume of that. The volume of the pyramid is the area of the base times the height, which is formula for any prism, but then we just multiply it by 1/3 or divide by 3. So let's say we have the same base and height as a cube. That's 6 by 6 by 6. I'm trying to draw that on the whiteboard. So 6 by 6 by 6. So we look at this here. Okay, the volume would be 6 to the power of 3, which would be 216 cubic centimeters for the cube. Now, if we do that, we know it's a cube, so we're going to do 6 times 6 times 6, but all the side lengths are the same, so we just do side length cubed, so to the power of 3, and we get 316. Now, if we want to find the pyramid, we could start all over, but since we know the volume of the cube, we know it's 1/3 of that. So we can multiply that by 1/3, or we can just simply divide by 3, and we get 72. 72 cubic centimeters. Cone is going to be similar concept, the cone relationship, just like the pyramid and the prism. It's 1/3 of it. It's going to be the same thing with a cone and a cylinder. And so if we have this cylinder that was a base here, and then imagine this one, draw. So we imagine we have a cylinder here. Well, if it gives us that the height is 30, the diameter is 20, so the radius is 10. Well, for the cylinder, we would just do pi r squared times the height. Which would give us 9,420 what was it? Centimeters, so cubic centimeters. But in this example, we are looking at a cone so it's going to be coming to a point. So it's not a circular base top and bottom. We have a circular base, but then it's coming to a point still. Radius of 10, height of 30. So we do pi r squared times the height, or we can divide by 3 before we do that since we're multiplying by 1/3, times the height of 30. Since this is all technically multiplication, we can do it in the order, but let's go ahead and do this. 3.14 times 100 is 314 divided by 3 times 30. So when we do all of that, we get pi r squared. 10 squared is 100, so we just kind of skip that step. You can put it as 10 squared, that's fine too. We divide it by 3 and then multiply by 30, or you can multiply 30, then divide by 3. Because 314 times 10, 30 divided by 3 is 10, comes out to be 3,140 either way. So that's what we came up with, because it's 1/3 of our cylinder. The cylinder we found was right there. And then the cone was a third of that, so we just divided by 3. So 1/3 base area times height. I know our reference sheet has it a little bit different. And so pi r squared times the height, which is the base area, so nothing changed, so times the height. That's if it's a cylinder, and then a cone, pi r squared times the height, same thing's down here. The only addition is we're multiplying by 1/3, or dividing by 3. Same thing. Okay, now a sphere, again, I know they went over this in the video, I don't know if you remember watching it, but a cone, 3 cones, that's why it's 1/3, 3 cones can fit in a cylinder with the similar dimensions. If we have a sphere, that obviously the diameter is the same as the height of the cylinder. So we think of a ball that we put into a cannon, it's touching all of the sides. That's what we're referring to. If we put a ball, like a golf ball, in a Pringles can, and it's not touching every side, or a tennis ball or whatever, it doesn't apply. Even if it's touching on the sides but not the top and the bottom, then this doesn't work. But if it's a cylinder, it will fit 3 cones in there, 1, 2, 3, and we can fit 2 cones in a sphere. Okay, so a sphere and a cone would be 1, 2, 3, which would equal that of a cylinder. And so using that to what we want to find, we know the volume of a cylinder, pi r squared times the height, and then 2/3 of that, and we can reduce, I know they went over this in the video, so 2 pi r, the height, again, would have to be that of the diameter, or 2 times the radius if this ball or sphere is going to touch top and bottom. So we get 2/3 pi r times 2r. Well, so we're walking through what we get. Pi r squared times the height. Pi r squared times 2 times the radius, because the height of that has to be the diameter, and the diameter is 2 times the radius. So that's where we get this. Move 2 out front to be our coefficient. Radius times radius squared gives us radius cubed. 2 pi r radius cubed. And then the volume of the sphere is 2/3 of that. So we do 2/3 times 2 pi r cubed. 2/3 times 2 gives us 4/3 pi r cubed. So that is our volume of the sphere. Again, having it on your reference sheet right away versus thinking about a cylinder and then a cone and then 2 cones equals a sphere, and then how do I calculate that? Well, you can go that route if you want. That's probably much easier to just go right to a sphere. 4/3 pi r cubed. And there we go. So if you're not really, 4/3 is a constant, pi is a constant. All we need to know is the radius. Plug that in, calculate it, and we're done. So let's look at this example. 4/3 pi r cubed, well, diameter is 20, radius is 10. There we go. So 4/3 3.14 pi times r, which our radius was 10, I believe. Yeah, so our diameter was 20. So 10 cubed. Sure everything's incorrect. 4/3 pi r cubed. Very good. And that's what we get. So 4,186.6 repeating, or 2/3 centimeters. So cubic centimeters. So we put everything in. Yeah, we got that. So they rounded it up to 4,200 cubic centimeters. All right, that practice set we will do together. Ooh, a lot of them. All right, when we get to class. And then our last one we're looking at today is volume, capacity, and mass in the metric system. And this is something I will let you write on your reference sheet. Okay, so you may memorize it, not need to. If you don't want to, that's fine. I would recommend doing it just so you have it in case you're drawing a blank on a test or something. So the relationship, and this is in the metric system, so this is why a lot of the medical field and places use the metric system, because there's this relationship that can be easily calculated. So let's start at the beginning. We have 1 milliliter of water has a volume of 1 cubic centimeter, and its I know weight and mass are not exactly the same, but it has a mass of 1 gram. 1 liter has a volume of 1,000 cubic centimeters and a mass of 1 kilogram. And so 1,000 cubic centimeters, all these are cubic centimeters. There's 10 by 10 by 10, there's 1,000 of them. It would contain 1 liter of water, which would have a mass of 1 kilogram. And a kilogram is about 2.2 pounds. So if you drink a liter of water, you step on the scale and then drink a liter of water and you gain weight, that's because obviously it has 1 kilogram mass. And like I said, I'll let you put those on there. I don't know. So 1 cubic centimeter equals 1 milliliter, which equals 1 gram. Multiply all of those by 1,000. 1 times 1,000, we're now at 1,000 cubic centimeters, which is equivalent to 1 liter, which is equivalent to 1 kilogram. So that relationship can help us out. That's why you've probably heard doctors or seen medical shows or something where they talk about, I need 5 cc's of this or 7 cc's of that. They're talking about cubic centimeters. That cc refers to cubic centimeters, and that tells the nurse or the doctor, whoever, how many milliliters or how much they need to draw up of a certain medicine. So that's what that is. Now, if we're looking here, we have an aquarium that's 50 by 20 by 30, and it's filled. Okay, it's filled up 30 centimeters. So how many liters of water would that be? This is exactly how it looked like. So I'll draw my own so we can. So we have this. So let's calculate the volume, 50 by 20 by 30. You can do that. It is 30,000, so the volume is 30,000, and it is centimeters, so cubic centimeters. And so that tells us that we're going to have 1,000 cubic centimeters is equal to 1 liter. Well, I have 30,000 cubic centimeters. That means I'm going to have 30 liters of water, and it's going to have a mass of 30 kilograms. Because 1,000 cubic centimeters is 1 liter, so 30,000 is 30. Liters and kilograms have the same ratio, so 1 to 1, so 30 to 30. Malika wanted to find the volume of a vase. She filled a 1 liter beaker with water and then used all but 240 milliliters to fill the vase. What is the volume of the vase? So there's 1 liter or 1,000 milliliters. So she had 1,000 milliliters or 1 liter. She filled it up, and those 240 milliliters she did not use. So the volume is 760. We do 1,000 minus 240. They show right there, but we do 1,000, which is 1 liter is 1,000 milliliters minus the 240 milliliters we didn't use, and we get 760. So we didn't calculate, we just used the difference to find that. And then B, if the mass of the vase is 640 grams, what is the mass of the vase filled with water? So we can go at 760 760 cubic centimeters. So that would mean 760 milliliters, which was 760 grams. Because 1 cubic centimeter is equal to 1 milliliter and 1 gram. And then we were told that the vase itself weighs 640 grams. So if it's 760 cubic centimeters, then it's 760 grams. I'm going to add those two together, and we get 1,400 grams. Or we could use the unit multiplier to convert that to 1.4 kilograms if we wanted to. Alright. We'll do that practice set together. That's it for this week. We'll see you guys in class.